Hey there, this is Arnav from Pebble, and welcome back to the Introduction to Linear Algebra series. In this video, I wanted to talk about inverses, which is a small deviation from plan, but I think this is pretty important, and we need to get it out of the way before we go into stuff like determinants and some of the other more complicated stuff that rely on determinants, because inverses used to, but now you really don't need it. So, what is the inverse of a matrix? Well, the way I want to define it is, let's say we have a linear system, right? We know, as we discussed in the previous video, which was lesson 1.2. If you haven't seen that, go check it out. Ax equals b. So we know this is how we can define a linear system as a matrix equation. And one thing that you might have noticed is that we can't just divide both sides of this equation like we could for a regular equation by a, because we don't know matrix. What is matrix division? We don't have an operation for that. Unlike something like 3x equals 9, where we can just divide both sides by 3, and we would get... I don't know if you guys heard that. That was my Alexa, who just randomly wanted to answer the question, 3x equals 9. So, good job, Alexa. X equals 3. That would be our solution. Right? We can't do that with matrices, because how do we divide something by a matrix? We don't have an operation for that. It's undefined. So we need to think about this in a different way. Well, what is division? Division is multiplication by a reciprocal, right? We're multiplying both sides here by 1/3, and we're getting x equals 3. So what if we could do something like the reciprocal of a? Well, in matrix land, we have defined an operation that is basically equivalent to real number reciprocal, and we're going to call that the inverse. Okay? And it's very similarly denoted, like the reciprocal of a real number would be denoted by raising to the minus first power. The inverse is also denoted like this. Okay? Inverse. Beautiful. So we can define this in also another term other than reciprocal. Let's say we have a matrix A and B is the inverse of it. When we multiply these two together, it equals I. And I haven't talked about I yet, but this is another type of special matrix, which I like to call the one of the linear algebra world, because whenever you multiply a matrix by I, it just equals itself. So it's very much the identity. It's the identity matrix. And so an identity matrix is defined by just ones on the diagonal and zeros everywhere else, and it has to be square. So this is the 3x3 identity matrix, and this is the only one. And then you could have a 2x2 identity matrix, just ones on the diagonal, zeros everywhere else, and this would go on for 4x4 and 50x50, any matrix, any dimensions, but it has to be square. Do remember that. And so if this is 1, right, and this is a times its inverse, which would be something like 3 times 1/3, which equals 1, right? Because these two are reciprocals, they're inverses of each other. So this is the same thing in the linear algebra world. And one thing to note here is that this is commutative, because A is the inverse of B and B is also the inverse of A. And so you might have learned, or you should have learned in matrix multiplication, that it's not commutative, but here you can see that these two do actually commute because they're inverses of each other, right? This is very easy to prove, and you can see that no matter in what order you multiply them in, because they're inverses of each other, you will be getting the identity matrix. Okay? And as you can see, if it's to be a square matrix, right, the square identity matrix, that means that they have to be square and of the same order. And so that means that inverses only exist for square matrices, but they do not exist for all square matrices. So if it does exist for a square matrix, then we're going to consider that matrix to be invertible, or another term you'll see often is non-singular. And then if they don't have an inverse, then we're just going to call it singular. Okay, and in this case here, this is basically just b is going to equal, to keep our notation, a raised to the minus first power, or a inverse. And you're not going to really hear anyone say raised to the minus first power, because it's not. It's just inverse denoted in that manner. Okay, so let's talk about an actual inverse now. So the matrix, let's say minus 2, 1, 1.5, minus 0.5. This is the inverse of 1, 2, 3, 4. How do I know this? Well, if I were to multiply these two matrices in any order together, that is going to equal my identity matrix for the 2x2. Okay, and you can try this out yourself and you can prove it. Okay, but in contrast, let's take another matrix here. 1 by 1/2, 1/3, 1/4, or something, and this is just the reciprocal of each of the values in our original matrix here. So I'm just going to denote this A, denote this B, and if I were to multiply this by A, you can see that this does not indeed equal 1, 0, 0, 1. You can go ahead and multiply this out. You can see that for yourself. And so since it doesn't, that means that this matrix, which I'll denote C, is not an inverse of A. Okay, now before we actually get to calculating inverses, I just want to talk quickly about elementary matrices, which are just an extension to elementary row operations. So let's say we have the identity matrix for the 3x3, and an elementary matrix is defined as just a matrix that has a row operation applied to it. So if I want to swap these two rows, which would be a row operation, whatever matrix I get out of that would be my elementary matrix for that operation. And then if I wanted to multiply a row by a scalar, let's say -2, then that would become my matrix for that. And then if I wanted to add this row to that times 3, then that would be my row operation. Okay, and that is pretty much it when it comes to elementary matrices. And so why do we use this? Well, this is how we find out the actual matrix of the actual inverse of a matrix, and we're going to be using this in an augmented matrix, which I'll show you later on. Okay. Don't know why that's still there, my bad. So let's take a look at well, how can we tell if a matrix is invertible? Well, it is if we can transform it into the identity matrix. So let's take the matrix 1, 2, 1, 0, 1, 3, and then 0, 0, 1. If we can transform this matrix into the identity matrix, that means that it is indeed invertible. Okay, and you can see that we can, because it's in a nice row reduced form. This is very easy to visualize. Just get rid of this 3 here, get rid of this 2, and get rid of this 1. Using this one and using this row column. And so that's very, very simple to show. And since we can, that means that this is inverse. Okay? And we'll define having an inverse as if and only if the matrix can be transformed into an identity matrix with elementary row operations. And that is very important to keep in mind whenever you're trying to figure out if a matrix has an inverse. Okay? So next order of business is actually finding the inverse. So the way we set up finding the inverse is we're going to put an augmented matrix here. And we're going to augment this with the identity matrix on the other side, right? So let's just take this at face value. Let's say that this is true. If you can transform it into an identity matrix, that means that it's invertible. So if I'm transforming this into an identity matrix, right, that means that I'm doing some operations that will undo my matrix, and we're doing operations, okay? And we know that row operations can be represented in terms of an elementary matrix. And when we multiply an elementary matrix by a matrix, then it'll perform that elementary row operation. So by that logic, we should be able to do a row operation here and then just store it in a different matrix. And then when we multiply these two together, we should just have inverses. So this left part would be our transformed into identity, and this one would be transformed into inverse. And I hope that made sense. It's just a very simple concept that we're just using the logic of our elementary matrices and taking this at face value in order to come up with our inverse. And I'll demonstrate this just to make it abundantly clear how this works. So let's convert this into our identity matrix. So we're going to do that by saying that we're going to get rid of 3 here. Sorry, we're going to get rid of the 3 here by multiplying by -3 times the first row and adding it to the second. And then we're also going to do that to the other side because we have to do it to the whole matrix, right? This whole thing is our matrix. So if we do that to the other side, then we should get something like this. And then we need to get rid of the second row we need to get rid of the 2 here, and also need to get rid of this -2 and make it a 1. Okay, so let's do those two simultaneously just to save time. 1 0 0 1, and then on the right side we're going to get -2, which is just that -2, and then 0, and then 3 by 2 because we're multiplying by -1/2, and then -1/2 here. Okay, so as you can see here, this has been turned into the identity matrix. And then this looks familiar because we just did it here. This is our... We proved this here, that this is the inverse of this matrix. And then we got the same thing here. So clearly by taking this at face value, the fact that the inverse exists if you can transform the original matrix into the identity, it works. So it just all proves itself, kind of. Okay? And hopefully this made sense, because what we're doing is we're performing operations on a matrix, and those operations are converting it into the identity matrix, which is basically just what the inverse does, right? It's a collection of operations, because in technicality, every matrix can be created using the identity matrix. And so we're kind of just using that to build back. And it's a very, very cool concept to think about once you can kind of grasp your head around it. So this sort of technique works for a matrix of really any size, although it does just get significantly more painful as you have more and more matrices. Okay, and let's look at an example of a matrix that cannot be taken as an inverse. Okay, so something like 1 2 2 4. And so this we cannot find the inverse of. Try to figure out why. I explained it earlier in the video, the general rule for this, but it's important that you try it yourself. Okay, so hopefully you've had a chance to do that. So one thing we can do is, you can see that these two rows, they're multiples of each other, right? This 1 and 2, just multiply by 2 and you get this row. So that is a big no-no when you're coming to find inverses. Basically, if I'll use a term called linear dependence, but if these two are linearly dependent, which means that if you were to multiply the rows by some scalar or some factor, then you could get one of the other rows out of it. That means they're linearly dependent, so they all have to be something unique. It's kind of like prime numbers, where the only way to get it is not contained inside the other rows of the matrix. So we can, when we're trying to find the row reduced form of this, we just get 0, 0, and then 1, 0, minus 2, 1. And so because there's a 0 here, you can't possibly convert this into the identity matrix, which means that it does not have an inverse, it's non-invertible, it's singular. Okay? And so one very important thing to note is that the inverse of a matrix is unique. Okay? So I love this proof. This proof is amazing. But if, let's suppose that we have two inverses, okay? And this is a type of proof that you'll see very often. So B and C are both inverses of A. So what that means is AB equals the identity matrix based on our definition. Since it's commutative, BA equals identity matrix, AC equals identity matrix, and CA equals identity matrix. Right? So that's just going to suppose that C going to equal C times the identity matrix, since that's just identity. But we know that the identity matrix is going to equal AB, right? And it's associative. We know that matrix multiplication is associative. It might not be commutative, but it is definitely associative. So we can associate these two instead. And then we know that CA is equal to I. So we get IB, and then we get just B, because I times B is just B. So C equals B here, which means that the inverse is always unique. Okay, and some other cool properties to note here is that the inverse of the inverse is just going to equal the original matrix. If you have two matrices multiplied together, and then you take the inverse of this, you actually get this weird looking pattern here that we will definitely look at later, because it's a very, very cool proof as well. And then the inverse of a transpose is just going to equal the transpose of the inverse, which I think would be a bit easier to think about. And then if we have some scalar lambda times a matrix, and then we take the inverse of all of that, we're just going to take the reciprocal of our scalar and then multiply it by the inverse of our actual matrix if lambda is non-zero. Okay? And so one other property, I think this is one of the final properties that we'll go over, is that if the matrix A is invertible in a system like AX equals B, if it's invertible, then the system of equations defined by this matrix equation has only one solution, because if you can do this, then you can say that A inverse AX equals A inverse B, right? And so these two will cancel out and you'll get X equals A inverse B. And since the inverse is unique, like we just talked about, we just proved, that means that this is always going to be the exact same X. So X is unique. X is unique. Okay? And so that concludes the basic introduction to inverses. And there's a couple other rules that basically will be pretty useful to telling if a matrix has an inverse that we'll be covering as they get introduced in later videos. But for now, that concludes inverses, and in the next video, hopefully we'll take a look at LU decomposition, which is a very interesting topic in linear algebra, definitely. Okay, I'll see you then.